My name is Martin Danelljan. I'm a senior researcher at ETH Zurich in Switzerland. So my talk is titled Deep Visual Reasoning for Optimization-Based Network Modules. So I want to start here by just briefly looking back at what we have become really good at in computer vision, right? So nowadays what we can do really well is to take a really big data set and train a huge neural network on it, right? And this was, of course, not easy to figure out how to do that, but this is something we have learned to do really well in the last decade, right? And then during inference, we will apply this network in a kind of feed-forward manner, right? So for example, if I'm doing image classification, I would feed in an image and I will get the semantic label as output. So this we can do now not only for image classification, but a number of fundamental tasks in computer vision. So for instance, object detection, right, where we also need to localize the objects, but also semantic segmentation, where we want to classify every pixel in the image. And now we can achieve quite astonishing results for these tasks. So this is, for example, results from our recent paper called Mask Transfiner for High Quality Image Instance Segmentation, where we can efficiently produce really accurate masks and object detection instances. But the question I want to look at here is that does this strategy really solve all our problems? So training on a very big data set and applying this kind of feed-forward network to our inputs. So first of all, what happens if we don't really have a huge data set, right? Or even if we have a huge data set, we might not have a lot of data for all our classes, right? The data set might be imbalanced. And if I want to create a data set with a really large vocabulary, I would definitely end up with lots of classes that are really rare, right? So for example, you can look at the Elvis data set as an example here. Another thing is, if we want to develop more advanced AI systems, right? We cannot just rely on the static knowledge, but we want AI system and agents to be able to sort of learn on the fly, to adapt and learn new tasks and concepts over time, right? And to be able to update their knowledge, adapt to new circumstances, and so on. And I'm not only talking about futuristic robots here, really. I mean, even quite basic AI systems require this. So for instance, if you want to do open world detection and segmentation, you need to be able to learn to detect new kinds of objects, usually during test time. Tasks such as image and video editing and semi-automatic annotation, right? Where you have an AI system interacting with a human that is telling it what to do, and you need to be able to update and adapt based on the inputs from the human, right? So then there are tasks that doesn't really fit well into this kind of feed-forward paradigm at all, to just concatenate all your inputs and feed it into a big ResNet or transformer. But tasks that require some more complex reasoning about different types of inputs. So an example is tracking, or many of the video tasks, for instance. So this was one of the reasons why tracking was actually quite hard to solve with an end-to-end deep learning framework initially, right? And it took another 4 or 5 years before we got really effective end-to-end architectures for visual tracking. But you also have lots of other tasks, I mean, classical tasks such as image matching, optical flow, and so on. So in this talk, I want to present how we can design deep neural networks that does some more complex reasoning with its inputs by minimizing an internal objective function, which becomes a form of online learning or reasoning, as we'll see, by the network. And I really wanted to cover a variety of tasks, so I don't have time to go deep everywhere, of course, but I will focus on a few particular ones. So we'll look at tracking, video segmentation, a bit at few shot segmentation, and multi-frame image restoration in the end. Okay, to start this off, I want to briefly talk about this work. It's a few years old now, but it was kind of the starting point for us in this research direction, and it serves the best to introduce what I'm talking about, and then we will build upon these techniques and generalize them to make it a quite general, powerful technique, as you'll see in other problems as well. So here we are dealing with visual tracking. So tracking comes in really many different varieties, but what I'm mostly concerned about here is what we sometimes call appearance-based tracking or general object tracking. Sometimes it's confused by single object tracking, but essentially we want to, or the problem is as follows, that we're given some example appearance of the object that we want to track. So it could be a bounding box given at some reference frame, like the initial frame of the video, track this object, right? And then we want to track this kind of object. So it's important to note that we want this to be something completely generic. So not necessarily a kind of object or a kind of class that was represented in our training set, right? It should be able to ideally generalize to any kind of object, any kind of object class, and so on. Okay, so probably I don't have to explain to you why just concatenating these two images and fitting it to a ResNet won't really solve our problem, right? So we need to think a little bit more about how we can solve this problem effectively. So if we were to design some kind of general framework how we could solve this problem, it could look something like this. So okay, so I take my reference frame where I will have my annotation already, right? I extract some deep features, and then I need some component, we'll call it here an online learner, that captures information about the target I want to track, right? So this need to somehow learn to recognize the specific object that we want to track. So it will output a model, some kind of model of the object that we're interested in, and then when we get the test frame, so a future frame in the video, for instance, we want to, first of all, of course, we also extract some deep features from there, then we want to apply our model, and we get some output. So for example, this can be like a heat map, a set of classification scores that we can use to find our target by finding the maximum on this heat map, for instance. So in reality, it's also a little bit more complex. We also want to do some bounding box regression and so on, but we'll stick to the simplest and most important components here. So the key module is really this online learner, right? That really needs to be robust and fast, right? Because tracking is also very much an online application. But we also want to train our whole system, our whole architecture end-to-end on some annotated video data sets. So we also need this component to be differentiable, so we can backpropagate gradients also to our deep feature extractors, for instance. So arguably the simplest thing you could do is what is called Siamese tracking. So here we, for this online learning component, what we do is essentially just crop the target region of the feature map, right? Either we crop in image space and extract features from only there, or we can crop in feature space, doesn't matter so much. But my output in either case would be a feature template of the target region, right? And then I could do some template matching in the feature space by just applying a cross correlation here, a convolution operation. So then I'm essentially computing similarities in feature space. So for sure, this is trivially differentiable. It's also a very fast operation, of course. The question is it robust enough for our purposes? And the answer is that it's really not. Okay, now something wrong with the slides here, but if we have similar objects like here, we will get some ambiguous output of them, right? And this is of course an important problem because often similar objects co-occur if you want to do tracking and so on. So we want to, it's most often not robust enough for tracking. So what we wanted to do was the following idea, that let's let this online learner instead predict the parameters of some discriminative classifier that differentiates between target patches, so foreground patches of our target object, right, and negative examples. That is background. Because remember, the previous Siamese approach wasn't even using the background information, the reference image. So here we're also exploiting the background image, and we want to train a discriminative model that can hopefully be much more robust than only doing similarity comparisons. Okay, so how could we do that then? So probably the simplest way to approach this is to train a linear least squares regression or linear least squares classifier. So here, so what do we have here? We have our deep image features, right? So here I have a sum as well, because in general we could have more training samples, not necessarily only one. So we could have more samples. For instance, when we track, we usually self-annotate and collect more data that we then feed into our memory to update our knowledge. Okay, and for each sample, we also have some label confidence function. So this is essentially an annotated heat map, right, where the center would represent where the object is, right? So what we want to do is to learn these filter weights here. We can see this as a convolution. If we have just a linear classifier, we want to learn these convolution weights by minimizing this error. So we want this convolution operation to produce a heat map looking like this, right, on our annotated samples. So we want to minimize this, this objective. And that was probably not the right button. Okay. Yeah, so it's a linear least squares problem, so of course we can minimize this. So I will come back to how we do it and why this can be done efficiently enough and that it's differentiable. But right now, you just have to take my word, and we would see this minimization operation as a neural network module, right? So we have some module that takes as input the features and the labels, right? And output the optimal filter parameters. I will say that this is differentiable, and we will see in the next work how we can actually implement this. Okay, so for now, we install this module in our network and predict optimal convolutional layers that we can then apply to our test image and get this heat map. And this works very well. Of course, as I said, this work is now a few years old, but we have a work that was presented at ECCV that still builds on these basic approaches, adds segmentation, some better bounding box regression, and so on, and is still now state of the art on this most challenging object tracking data set called AZOT. Okay, so instead of lingering here, I will now want to see how we can transform this to a more general approach that you can use as a neural network component in a wide variety of applications here. So I'll do that by presenting this next word called learning what to learn for video object segmentation that we presented in last ECCV. So the task itself, video object segmentation, is essentially the same as tracking, but instead we want to output a segmentation mask of the target, right? So from that perspective, it's much more challenging. We need to capture much more detailed information about the target object. And again, this can be we want this to be any kind of object, right? So not necessarily something that is that we find in our training set, but it should learn to generalize to completely novel objects online. And as reference, we're given a segmentation mask. Actually, we can still do this even if we're only given a bounding box here, but I will present the case where we're given a reference mask in, say, the first frame. So let's first try to design an approach inspired from this tracking approach I just presented then. So we start from this reference image, this annotated image. We extract some deep features again, right? And then we want to learn this one convolutional layer that I presented before, right? So the only difference here is really that our target is now the segmentation map, right? So the segmentation, instead of the heat map, we will have the segmentation as the target of our optimization. The other changes are just changed notation to tau here, just to keep you awake in the morning. Okay, so the optimization problem still looks the same. Of course, we can do this. So let's now go to the test frame where we want to segment our object. We apply our learned convolutional weights, right? Now, as you might imagine, just applying a single convolutional layer on top of some deep features won't really give us an accurate segmentation mask at all, right? Might give us something really robust, but it's not really accurate at all. So what do we do about that? We, of course, use deep neural networks. So we feed our core segmentation mask into some segmentation decoder network. It will use this coarse mask as a guide, right? And then it will also use some shallow, high-resolution deep features for it. It will use its learned segmentation priors to produce a really nice, detailed segmentation mask. And this approach works quite well. It's not really state-of-the-art, but it works pretty well. So what we then observed when we came to this stage was that, okay, if we look at this now suddenly this module is in the middle of our deep neural network, right? We're not really online learning the final output layer, like the final classifier online as you would do in a few-shot problem. But now it's embedded deep in the middle of our neural network. So here there's nothing really constraining us from simply outputting one segmentation channel, right? One segmentation layer. So why not try to train multiple filters that would produce some high-dimensional, more richer representation about the segmentation mask and about the target object, right? So this could give more detailed information to the decoder that it could use to more accurately produce the final mask. Okay, so this sounds like a sensible idea, I hope. So let's look at what we would do in the reference frame in this case. So the question now becomes, of course, what shall we use as the target for this optimization process? I mean, previously we used the segmentation mask, right? But now we want to output this kind of abstract intermediate representation of the mask, right? So we don't really have any labels for this. So I mean, what should this be? So as you might guess from the title is, of course, that we should also learn what this online learner should learn. So what kind of representation it should learn, right? Which was kind of the key idea of this paper. Okay, so what do we mean with that, and how can we actually implement this? So what we do is that we introduce this encoder network that takes the mask, so the annotated mask as input. It can actually also take other things. We can also input the features as well, can be useful sometimes. So it will take this reference annotation and produce some multi-channel output, more high-dimensional output. We don't really know what it is. It's some learned space that is the target for our optimization problem. So while we're here, we can, of course, we could do something even more, or we can build on this even more. So what we can additionally do is not only output what the target should be, but also a weighting of this optimization problem. Because something we have is that, okay, so both different examples, so different pixels, different frames might have different importance, right? Or different certainty, right? So we might want to weight them differently. Or for instance, that the target region, the foreground region might be more important for learning than the background, right? So we want to weight it even more, or edges might be more important and so on. But all of this stuff is something we don't really want to hand code. So, but this gives us the opportunity to learn this, right? So similarly to the label generator, we will have this weight predictor just inputs the segmentation and will predict the weighting of this objective. And so now we minimize this problem. As you can see, this is still a linear least squares problem, right? and this would produce the parameters of our convolutional layer. So now let's look at how we actually implement this optimization module. There are actually multiple ways of doing it. You can try to use a closed form solution, but the optimization problems we're doing here are really high dimensional and so on, so it wouldn't really be efficient to do that. You can do something that is called the implicit function theorem to directly backpropagate your solution and so on. I won't really go into that. But the simplest and most effective and efficient way of doing it that we find for this scale of problem is an iterative optimization, applying an iterative optimization method and then unrolling those iterations. So for this, we need some iterative optimization method, right? And the most common optimization, or the optimization approach I hope all of you know, is gradient descent, right? That we simply take a step in the negative gradient direction with some hand-tuned step length in our optimization. So we would set this alpha by hand, right? But for our application, it's of course important with efficiency, right? Not only because we want it to be fast during inference, but remember that we're also running this optimization during training, right? So in each forward pass, we need to optimize, learn this filter, right? And we also then need to be very efficient to be able to train it effectively. And also to minimize the memory consumption during training, we need to have as few iterations as possible. So convergence speed is crucially important if we want to make this to actually work for multiple reasons. So you can do a quite minor change to this optimization algorithm that transforms gradient descent to a really, really powerful optimization method, especially for these kind of problems that are convex or sort of nearly convex. And that is to do what is called steepest descent. So instead of just hand tuning our step length, we would try to find the optimal step length in each iteration. So the step length alpha here is achieved by minimizing this one-dimensional optimization problem, right? Where we search for the optimal step length in the gradient direction. And how do we solve this? So the nice thing, of course, we have a one-dimensional optimization problem now in each iteration, so this should be more efficient to solve. But if we have a quadratic problem, which we had, so linear least squares problem is of course a quadratic optimization problem, then there is a very simple closed form solution for this alpha that we can just plug in to our optimization algorithm. So it just involves taking the dot product of the gradient, then we have some gradient Hessian product over here, right? So now you might be wondering, okay, do I need to derive by hand what my gradient of my loss is and the Hessian and so on? And the answer is no, because you could do that and plug it in, but things like PyTorch and JAX all have iterated differentiation, right? So actually you can write this as a very general algorithm and just do iterated or higher order derivatives, and it actually equally efficient as essentially as implementing this by hand, and it works really great. Another thing, if you don't have a quadratic optimization problem, then you would just do a quadratic approximation, right? So you could do a Newton approximation, which is just a second order Taylor expansion of your loss, right? Or if you have still nonlinear least squares, you would usually do a Gauss-Newton approximation of your loss. So this definitely supports nonlinear and even non-least squares problems. So if you have a softmax classifier, it's easy to apply this approach as well. So visually, just the way you can think about this is that, so even if my original problem then is non-quadratic, I'm at some point, right? And then I look in the gradient direction and make a quadratic approximation in the gradient direction, and then I jump to the minima of this sort of 1D slice quadratic approximation of my optimization problem. And just to give a visual representation in your head what this optimization algorithm is doing, right? So this converges incredibly fast compared to standard gradient descent. And in most of the problems, we actually just need a handful of iterations to get to really good result here. Because in all our applications here, we don't really need to find the very, very optimum. And actually, it might not even be advisable to find the very optimum because you might have overfitting and so on. So we just want to minimize this to sufficient extent to integrate this knowledge into our solution. Okay, so let's draw our full pipeline in the end. So it would look something like this then. So we have our reference frame and annotation. We will run the online learner given the label generator and the weight predictor results. This will give us the weights we then apply to the test frame. Produce this segmentation representation, we'll feed it in some decoder network, which will give us the final prediction. So one huge important advantage of this optimization-based formulation here, the way we model the problem, is that we can really easily update our model. So when we made a prediction, we can add our prediction to our memory, just add another term, right, to our objective, and then run our optimizer in the next frame for a few more iterations to update our model to this new data, right? And so this update is really important for many applications, especially things like video object segmentation. As the object changes and so on, we need to capture more and new details about the object. And also when we do training on offline then on our large video segmentation data sets, this is also really simple. We just run our full pipeline as is, basically no change from inference, and you just take your favorite segmentation loss and apply it between the ground truth and your predicted segmentation map. Yeah, and these are how our results look like. So if you're interested in our tracking and segmentation work, they all are at this GitHub called PyTracking, where we have, yeah, essentially all our works and many that I won't present here. So I will briefly wanted to talk about this work that we'll also present now at this ECCV. It's called Gaussian process regression for few-shot segmentation, because it generalizes these concepts in another, I think, very interesting and useful way. So I won't go so much into detail here. Unfortunately, I don't have time to do that because I want to come to the next work. But so few-shot segmentation, here we're given a few training examples, right, for semantic segmentation. So for example, okay, we don't know what the cat is, but I will give you 3 examples where I have segmented the cat. And then I get the new image and I want to be able to segment this object, right? So it's few shots learning for very, very few examples. And as you might understand, this is really challenging, right? That especially in our background might appear all kinds of new types of objects and stuff we haven't seen, right? Also from these few examples, it's difficult to generalize because it might have a new appearance, a new color, and so on and so on. So what we did in this work was to generalize this online learner to a Gaussian process. So if you know something about Gaussian processes, a useful way to see it is as a generalization of linear regression. So you can generalize linear regression to a Gaussian process, essentially. So the question is, okay, why is this useful? It's useful because in addition to the prediction that we get otherwise, of course, which would be the expectation value of the Gaussian process, we also get the variance. So the variance would represent the uncertainty in our online learner, right? So where it's not really certain, where we don't really have data to say something concrete, but the Gaussian process can give us that output uncertainty. So why is that useful? Then this can serve as a very good cue for our segmentation decoder, for instance, in this case, right? And it can learn to draw conclusions from this uncertainty. Like, for example, you would think that in general, background is more uncertain than foreground, right? Because in background, we have more variability, more new things can appear that we really haven't seen in our support set, and so on. So it serves as a very useful cue, and our uncertainty decoder can learn to also reason using this uncertain information captured in the variance to do a better prediction. So another advantage here, again, due to this explicit formulation of the learning is that compared to other state-of-the-art method, we are scaling really well when you increase your shot size. I mean, going from one training example to multiple training examples during inference. And this is actually something that is quite hard, and not many approaches really care about, but we scale really well. Of course, you want a system that, okay, if I give you 2 examples or 3 examples, I should be able to perform much better than if I would only give the system 1 example of the object. And yeah, so lastly, you see that the data sets used for this can be really challenging. And even as a human, it's quite difficult to see what we're supposed to segment. Often it's some obscure thing in the background of the scene and so on. So, okay, anyway, let's go to the last work here. So it's called Deep Parameterization for Multi-Frame Super Resolution and Denoising. So I really wanted to go into this because the problem here is quite different. So now we want to do multi-frame image restoration. So this we presented in last year's ICCV. Okay, so first to give you some background, right? If you take an image with your phone, especially outside, if it's a bit dark outside, or if you do it inside. So if you actually look at the raw output, so the raw sensor output from your phone, you would see that it is really surprisingly noisy and blurry and so on. So what can we do about that? Of course, we could try to train a deep neural network to restore this one image to something deblurred and super resolved and so on. But in one image, we still have very limited information, right? So it can do some improvements, but not really much. So what actually most phones, especially if you have a bit newer one, is doing nowadays is to take multiple frames in rapid succession, what is called a burst, right? So instead of taking just one frame, it takes 5, 10, or even 15 frames within half a second or so. And then the advantage of this is that, of course, each individual capture has an independent noise sampling. But moreover, when you're holding your phone, you're constantly shaking just a little bit or moving just a little bit. So we'll also get the new sampling of the scene because the pixel grid is shifting around just slightly. So we can also use this to sort of go beyond Nyquist sampling theorem, right? So then the problem is to try to merge all these images, this burst of images, into one much better image. So again, we have these challenges if we just want to throw this into a deep neural network. As I said, we have this unknown motion, which we want to exploit, right? But still, I have these misaligned inputs, right? And just concatenating things won't give me really an effective fusion, preserve enough details of the individual images and so on. So what we did in this work was to a bit look back and see what were people doing before deep learning. So one paradigm is called model-based multi-frame image restoration. So what do you do here? Essentially what you're trying to do is to model the whole image acquisition pipeline. So we start with original, kind of an ideal image. And then we model each step, right? So first of all, we have some motion in the scene, right? Both in the scene, we could have some camera motion, a combination of that. So we could model this using a homography or even a pixel-wise optical flow if we want. Then we have sort of the physics that is going on inside our camera, right? We have lens blur, we have downsampling, mosaicing, and so on, which we model to this module H here. And lastly, we have noise, different kinds of noises. Often we could, for now, model it as just additive noise. So we have usually shot noise and sensor noise and so on. Okay, so mathematically I could write this forward process like this, right? Okay, so how could we use this to then do image restoration? Well, say I have an estimate of my final image. So I would feed it into our model, assuming that we know everything. So I'll get my synthesized observations from this estimated image, and then it's an optimization problem, right? That I want to minimize some reconstruction error between my actual observations and my synthesized observations from my original image. And again, what most people were doing was to use a least squares objective. So why would you use least squares objective? Well, of course, it's optimal in negative log likelihood sense if you have Gaussian noise. So if we assume Gaussian noise, it's sort of the correct thing to do in the sense of negative log likelihood minimization, right? And moreover, you would usually add some kind of regularizer here to input some priors into your optimization as well. You could use an L1 prior or something like that, or total variation, or yeah. Now, as you see, this is a very principled way of trying to model the problem, fusing all the inputs, using the information we know, and so on. So it's a really nice method, but of course it has a number of shortcomings. So as I said, we really assume Gaussian noise, which is often not really correct when you deal with images in this way. We need to manually set this regularizer, which can be very difficult. Which one should we use? Important, we also know that this degradation function h is known, right? Which definitely is not the case, and it can be really difficult to model, and then I need to calibrate it somehow to learn the parameters, which is difficult. And lastly, we cannot really only handle quite simple h and r's here in order to still be able to solve this optimization problem. So what we wanted to do in this work is to, of course, try to resolve all these issues while still keeping this concept of a very principled fusion and modeling of the problem. So now, instead of just showing you our final architecture and try to motivate that, I wanted to do it a bit differently now, that we will try to derive our approach step by step, starting from this classical model-based approach that I presented, and look at one of these downsides sort of one by one, and come to our final solution step by step. Okay, so let's start with this Gaussian assumption problem, right? That we have a least squares loss directly in image space, right? So in order to address this, we introduce an encoder network. So the idea here is that we map the observations to some deep space, right? We have some learnable encoder network, and now it will be a least squares loss in this deep space, right? So we'd have a Gaussian assumptions there, and so essentially this encoder could learn then to map the data or where the error distribution is approximately Gaussian. So we could learn this. Okay, so that is the first step. Now, next, okay, let's do a change of variables of this optimization problem, and then I will explain why we do that. So instead of minimizing over our final image pixels directly, why here we would minimize with respect to some latent variable z, and then those are related by a learned decoder network. So we would predict our final image by running it through this decoder network. So okay, we changed the optimization variable in our optimization problem here, so which will give us the decoder here and here, right? Okay, so what is the advantage here? What have we gained here? Well, first of all, this decoder could learn priors in the prediction, right? Because it acts as a final step. We could bring in some of the power of deep learning to help it to learn these prediction priors that we want to get a better output image. So also importantly now, because the decoder is there, it's composed with a regularizer, we could replace this with a very, very simple regularizer in the deep space. So again, the idea here is that the decoder will control and learn the deep space, right? So, or this latent space. So it should be able to learn a latent space where a simple regularizer, just an altitude regularizer, makes sense. So that is the idea here. We can use a simple regularizer, and also this kind of variable change will also help our optimization, because you can see it as a preconditioning. Okay, lastly, we will try to sort out the mess we have here now in our optimization problem. So first of all, we will assume that the decoder and this motion, okay, I didn't really say this, but what is this motion? This is actually an image warping, right? I have some optical flow, or I have a homography, and then I warp my image according to that. So this is an image warping operation given this motion, right? So I would assume that the decoder and this warping operation commutes, so we can switch the order between them. So how can we make that assumption? Okay, so let's think first in the simplest case, where the motion is only a pure translation, image translation. So then probably if we have a convolutional neural network, it is translation equivariant, right? And equivariance basically means that your operations commute, right? That if you have a shift in your image, you'll also have a shift, the same shift in your CNN output. I mean, there are some assumptions there that we have a pad-free convolutional network and so on, but it sort of makes sense in the case of translation. Okay, but of course we don't have a pure translation, but in practice we always have something that locally looks like a translation. If I look locally, it can often be, or more or less always, well approximated with a translation. Of course, I won't have just pure random motion in my scene. So it will be locally smooth, locally a translation. So approximately this is a good assumption. But moreover, again, that remember that we will learn our decoder, right? So it can also learn to better satisfy this constraint. So through that, it also makes sense that it can learn to satisfy this constraint that we impose here. Okay, now so now we have this sequence of 3 networks composed, right? So let's say I want to also represent my degradation function as a deep network. So we can call this just G. So the idea now is that, okay, so I talked about E and D, right? Not really talked about H. So we would like to learn that. But now when I made this change again here of not really a change of variables, but just this notational introduction. So anyway, we're learning all these 3, right? So why not learn, and this is the additional thing. So why not learn G directly? That is just the composition of all these 3 networks. Because we anyway have this unknown network mapping in between this decoder and encoder here. And okay, so then I can learn this G directly, but now I can also put some constraints on this G. For example, that, okay, it should only be a linear kernel, so linear network, essentially. And how does that make sense? I mean, again, now we have full freedom to learn this latent space and this encoder space, right? So again, these 2 networks should learn to satisfy the constraint that we put on G, right? I want G to be linear, to have a simple optimization problem, and then this E and D should be learned to satisfy this constraint. So the big advantage here is that we can introduce this G. We just restrict the G to be a linear network in the simplest case. So we're back to a convex or even a linear least squares problem, right? And since this is in this latent space, if we would have pulled up the same network in image space, it could represent a really complex operation. So it's linear in deep space, but in image space it would be a very nonlinear mapping, right, through this relation here. Okay, and lastly, we do similar as we did before and introduce this learned weighting, right? Because notice here again, I have a lot of so I might have varying noises in the image. I might have errors in my motion estimation. Maybe one image in my burst was completely blurry and so on. So this one I want to then completely downweight. So again, these are things we can learn, and we can learn this weighting and just input whatever we want, right, to learn this weighting properly, including the motion and noise parameters, etc. Okay, so the final optimization problem looks similar to what we had before. There is a kind of slight change that we have before we were kind of learning the kernel, right? But now notice that we're learning the whole kind of image or latent image, this Z image. But it's still a linear least squares problem. The steepest descent algorithm works great applied here. We just need to run a handful of iterations, and it's really really fast when we unroll them. And if we just write our whole pipeline as a single neural network, it would look something like this, right? We take our observations. First, we run the encoder individually for each observation. Then we have our optimization module where we input the flow estimation. So here we use another deep neural network to estimate optical flow between the images which we input. And so the output will be our this latent image, which we feed into the decoder, which will give us the final image, restored image. And training, yeah, as before, we will just train it completely end to end. We have some ground truth loss. I mean, there are some complications in practice here because our ground truth is not aligned, so we need to introduce many techniques here to take care of that, but I will just refer to the paper if you're interested in that. But basically we just have this final or loss on the final output given a reference image. In our applications we capture this using a DSLR, or you can have used synthetic data and so on. Okay, so just to visualize the results, so here we are doing restoration and super resolution on real data. So this is captured with an Samsung S8, I think. So on the right side you would see the input, on the left side you would see our restored image. So this is the input, and this is the details you get by doing our burst, super resolution and restoration. And here we are comparing to the right then with a single frame deep neural network with similar size and parameters and so on. So you still, especially if you look here, the aliasing pattern and the amount of added details we get. And also compared to the previous state of the art, this was the first work essentially that was doing deep super resolution or burst super resolution. So we get much more detail. This is also on real data. So we also apply this for burst denoising. So then we have this input. This was the previous state of the art. You'll get lots of artifacts and color artifacts and so on. And our output is almost, in a sense, almost better than the ground truth, because the ground truth actually also has some noise in it. Okay, so before I come to the conclusion, I will just mention that we have some other tasks where we're applying these optimization-based models really successfully. So if you're interested, you could do few-shot classification. We have looked at converting bounding box annotations to segmentation in video, where you need really powerful or aggregate information across both time and space. And also matching and optical flow is something that we have looked at in this work. So to conclude, what I presented is that you can input these objective functions in your deep neural networks and use them as a form of reasoning in deep networks. as you've seen, it's very general, works for many different kind of tasks. Either you can use explicit formulations like learning a classifier, or the whole objective and also part of the optimization procedure then is completely learnable. And we'll look at several applications. I didn't really have time to go into it, but there are strong relations to things like attention and transformers here if you're interested. And you can ask me questions about that later. Okay, so thank you very much, and we might have time for some questions.
First, thanks for the amazing presentation. And then my question is, when you're doing a quadratic approximation, it needs quadratically more memory than a linear approximation. In this scenario, how do you tackle memory management problems for really huge neural networks?
No, so actually a quadratic approximation doesn't really need quadratically more memory. It depends on how you implement it. So if you do it kind of naive way and directly build the whole Hessian matrix, then yes, as you say, it will be quadratically more complex. But you have to remember that you don't really need the full Hessian. The only thing you need to do is evaluate the product between the Hessian and the gradient. So you only need to implement this operation. So it's kind of similar how you can do conjugate gradient without having access to the full matrix you're optimizing. So the answer is that if you implement it correctly, you don't need actually quadratically more memory, because you don't need to build your whole Hessian matrix. For example, if you have a convolution and in your operation and you build your Hessian matrix, essentially that will also be a convolution, or yeah, some also transpose convolution and so on, or yeah, a transpose convolution composed with a convolution, right? So then you just implement it like that, and you don't build the whole Hessian matrix and do a matrix multiplication there.
Okay, thank you.
Thank you.